Hello everyone, welcome to today's webinar. I'm Linda Wang, Senior Correspondent at Chemical and Engineering News, and I will be moderating today's event. This webinar is titled Separation and Characterization of Complex Biomacromolecular Architectures and is being sponsored by Wyatt Technology. The presentation today is being sponsored by Wyatt Technology, a leader in cutting-edge instrumentation and software for determining absolute molar mass, size, charge, and interactions of macromolecules and particles in solution. During the presentation, we will hear from Albina Lederer, head of the Polymer Separation Group at the Leibniz Institute for Polymer Research. Albina received her PhD in physical chemistry from 1999 from the Max Planck Institute of Polymer Research, Mainz, and the University of Mainz. Her research focuses on nanostructural aspects of dendritic polymers, novel separation techniques, and intermolecular interactions of branched and biofunctional architectures, and in situ characterization of responsive polymer systems. I'll now hand the presentation over to Albina.
Thank you for the introduction and welcome to this webinar also from my side. Today's talk is separation and characterization of biomacromolecular architectures as a main topic on which we are working at the Institute of Polymer Research within the Polymer Separation Group where I am coming from. Why is separation and characterization of biomacromolecular architectures and specifically of macromolecules so important? Polydispersity in macromolecular systems is a main issue which has to be taken into account when tuning material properties. Polydispersity in terms of macromolecular weight is the usual one we are talking about, and this means that we have different size of the polymer chains and different length. When we are talking about polymers, we have to take into account also their topology. Do we have branch polymers? What type of branching do we have? And how this branching influences the functionality, the number of functional groups, and the interaction properties. This issue is coupled directly with the conformation of these polymers, and therefore we have to find techniques and methods how to understand them and to analyze them in terms of molecular weight too. Therefore, today's talk is focused on three main topics. The first one is theoretical and technical options for conformation analysis, in which I will show you some basic theoretical equations in order to understand conformation and how to combine techniques in order to solve these equations. The second section is conformation analysis of simple macromolecular architectures, in which I will show you some examples on macromolecules with different topology and how can we understand this topology based on the theory and the techniques I'm showing you in the first section. And finally, based on this knowledge, we can go to more complex systems as biomacromolecular systems, in which not only conformation but also quantitative analysis of these structures will be done. The main method for conformation analysis is the static light scattering. Static light scattering gives us the relay ratio, which is coupled with the molar mass and the radius of duration. Now, having molar mass and radius of duration from this method, we can solve the equation called scaling law. If we have different molar masses and have the molar mass for every species we have the molar mass, the radius of duration, we can obtain the scaling parameter. And the scaling parameter is directly coupled to the conformation of our particle or macromolecule. If we, for example, have a scaling parameter of 1, we can talk about rods. And having a scaling of 0.33, we have theoretically uniform parts field. Additional information which we can calculate from the molar mass and radius of duration is the apparent density. The apparent density is quite important parameter talking about conformation and compactness of macromolecules or particles. Now we can combine static light scattering with dynamic light scattering, which gives us directly the so-called rho parameter. The rho parameter is the ratio between the radius of duration and the hydrodynamic radius, which have different nature and therefore can give us information about the shape of our particles and macromolecules. And another way to use static light scattering together with viscosity, for example, is using the specific viscosity or directly the reduced viscosity at concentration 0, which gives us the intrinsic viscosity. The connection between the intrinsic viscosity and the molar mass is another equation, which is the so-called Kuhn-Mark-Howing equation. The Kuhn-Mark-Howing parameter alpha is also a way to describe the conformation of the macromolecules or the particles, and the values of alpha, which are interesting for us directly for different macromolecules, are shown here. Additionally to this information, we can obtain also the viscosity radius out of the intrinsic viscosity in the molar mass using this equation. So you see that using viscosity detection, static light scattering detection, and dynamic light scattering detection, we can obtain three different radii: the radius of duration, the hydrodynamic radius, and the viscosity radius. Now, at least two of these parameters of these equations are molar mass dependent, which means that we have to obtain series of molar masses out of one sample, and this is usually not very easy just using different synthetic conditions. Usually we have to take a fractionation. Preparative fractionation is a well-known method to obtain fractions according to the molar mass. The principle of this fractionation is based on the different solubility of different molar masses, so using a solvent gradient we can obtain the fractions in different molar masses. However, this fractionation method is obtained with big effort, though one advantage is that we can obtain fractions in amount big enough in order to make additional analysis on the fractions, as for example microscopy, spectroscopy, different separations, additional or scattering methods. One faster method to obtain different molar masses is the size exclusion chromatography. This is an entropy-driven separation, as you may know, and this chromatography, the size exclusion chromatography, works by separating only after one injection of the sample in fractions with very low distribution, narrow distribution according to the molar mass. Another method, which is relatively new compared to the chromatography, is the field flow fractionation. Within this method, we have not a channel filled with material with different pores, as is the case of chromatography, but we have a channel within the particles are separated according to their diffusion properties. This means that, first of all, we can separate broader molar mass ranges compared to size exclusion chromatography, and additionally we don't have strong shear forces as it is the case in size exclusion chromatography or in chromatography in general, because we have here a channel which is not filled with any material, and this reduces the shear forces used during this separation. However, this method has, of course, also disadvantages, and this is the molar mass range below about 5,000 Daltons. Within this range, the macromolecules are, at least in case of asymmetrical field flow fractionation, not possible to be separated because they are penetrating the membrane of this channel. This is not a problem when using size exclusion chromatography, which works very well from very low molar masses up to several millions. However, working with bigger complexes, and especially with biomacromolecular systems, higher molar masses have to be taken into account, and here field flow fractionation is really very useful. Now, having already two separation techniques, size exclusion chromatography and field flow fractionation, which are working fast, separating molar masses into very narrow fractions, we have now to find a method how to combine these separation methods with detection, as I showed before, light scattering, the specific viscosity detection, and dynamic light scattering. This coupling between one of the separation techniques, size exclusion chromatography or field flow fractionation with three detections, can be done very well, as you can see here in our lab, and delivers quite interesting results in terms of macromolecular separations, as well as in terms of characterization of biomacromolecular systems, which I'm going to show you in the next two sections. Let me now start with the second section of this webinar, the conformation analysis of simple macromolecular architectures. With simple macromolecular architectures, I will mean within this talk polymers which can be different in their topology, but not very complex in terms of chemical structure. One example of very strongly branched polymers are the dendritic polymers. One example is dendrimers, and the dendrimers has a perfectly branched structure with only dendritic units as well as terminal units as polymer units. Hyperbranched polymers have another type of synthesis which leads to statistical type of structure in which not only dendritic and terminal units but also linear units are existing. They are not perfectly branched, and they exist also in very broad molar mass distributions within one sample, and additionally they can also have distribution in terms of branching degree. The usual statistical branching gives us 50% degree of branching, but we can have also different other structures if non-ideal statistics is resulting from the synthesis. One example of chemically very simple polymers are the polyolefins. However, polyolefins are not very easy to be characterized, taking into account their low solubility, at least talking about low or high density polyethylenes, which are classical polymers. Therefore, we have to make their analysis at 150 degrees in trichromabenzene. These conditions can be achieved indeed in a high temperature size exclusion chromatography system in order to obtain additional full conformation information about these polymers. We need to use a static light scattering detector, which in this case is called MOLS, multi-angle laser light scattering detector, which is coupled to the quasi-elastic light scattering or the dynamic light scattering, in other words. And additionally, we have a concentration detector, which is needed in order to understand, to analyze the static light scattering data. And we have also the viscosity detector. So we obtain finally 4 different chromatograms dependent on the different detectors. Using all this information, we can finally calculate our 3 different radii, the radius of duration, the hydrodynamic radius, and the viscosity radius. Now, having this information and also, of course, the information about the molar mass, we can finally plot these results according to the scaling law and also according to the Kuhn-Markowing equation. The scaling law gives us the scaling parameter or the slope of this plot. And here we have the alpha exponent. You will see here that we investigate different types of polymers, linear polymers, linear LDPE, as well as linear polyethylene made by the so-called chain walking mechanism, and want to compare these rather trivial polymers with novel type of polymers which are synthesized by the chain walking mechanism at different conditions, different pressure, different catalysts, and also different temperature. So compared to the linear polymers, the chain walking polymers, or the polymers synthesized by chain walking mechanism, show clearly much more dense structure, which can be explained with their very strongly branched character. In other words, the combination of the size exclusion chromatography together with viscosity and static light scattering detection in this case can give us direct information about the conformation of this novel type of polymers. Here I will show you one another example of differently branched polymers based on another synthetic procedure, namely polycondensation. Using this procedure, we obtain differently branched structures starting from 0% degree of branching, which means linear structure, and we can go up to 50% degree of branching, typical for hyperbranch structures. Using the combination of static light scattering, viscosity detection, and of course for separation according to molar mass, we can finally obtain, again, very good information about the Kuhn-Markowing behavior of all these polymers. This Kuhn-Markowing behavior gives us the alpha parameter, which is clearly decreasing with the degree of branching, starting at 0.6 for linear polymer, which is typical for statistical coil, theoretically, and going down to 0.35 for 50% degree of branching, typical for hyperbranch polymers. When we go to higher degrees of branching for the so-called pseudo-dendrimers, we even can achieve values which are very, very close to a hard sphere. About pseudo-dendrimers, I will talk in the next few slides. Pseudo-dendrimers are one example of the so-called dendronized polymers. Now, up to now, we talked about differently branched polymers starting from linear and going up to hyperbranch or dendritic polymers, but we can obtain even more complex combinations of structures within one macromolecule. These complex polymers or macromolecular hybrids are, for example, the denpoles, in which we are combining linear polymer with dendrons, which can give us very, very strongly branched and highly functionalized polymers. Additional example is the combination of hyperbranch polymers with dendrons, which gives us pseudo-dendrimers in different generations too, depending on the generation of the dendron. One example of pseudo-dendrimers is again a polyester, in which a hyperbranch polymer is forming the core, and we can build on the top of this polymer, on the top of the functional groups, the first generation, the second, the third, and the fourth generation pseudo-dendritic dendrons. Finally, what we can obtain by building these pseudo-dendrimers in different generations is first of all an increase of the functional groups, starting with 50 functional groups in case of the hyperbranched core, and going up to 800 for the fourth generation of pseudo-dendrimer. This increase of functional groups is very well known from dendrimers, finally, but what we can achieve here is also very, very strong increase of the molar mass, which cannot be achieved with typical dendrimers. Furthermore, we have degree of branching in this case, which is slightly decreasing with the next generation because of spherical reasons, but we are still at very, very high degree of branching, higher than 85%. Now, what we can obtain about these pseudo-dendrimers and what is interesting to us is, of course, their conformation and their shape, depending on the generation number and the functionality. Interestingly, after the calculation of the intrinsic viscosity coupling of separation method, defining the molar mass by light scattering, and the intrinsic viscosity, we can directly obtain the intrinsic viscosity of every single generation. And this intrinsic viscosity is dropping independently on the increase of the molar mass depending on the generation number. The specific behavior of the intrinsic viscosity was already observed for dendrimers after the 4th or 5th generation. Now, much more interesting is also the dependence of this intrinsic viscosity on the molar mass in terms of Kuhlmann-Hawing exponent alpha, which shows that with the generation number we have decrease of this alpha exponent, showing again very compact structure with every single generation, but also we have increase of the apparent density, which confirms this kind of behavior and can be obtained also from the intrinsic viscosity, taking into account this equation. What is interesting here is that the intrinsic viscosity as well as the Kuhlmann-Hawing exponent is absolutely not dependent on the functionality, taking into account two different functional groups, OH terminated and Dilute terminated functional groups. Now, pseudo-dendrimers have obviously very specific segmental structures, which was the main topic of this study, and we showed by molecular dynamic simulations that the hydrobranch core is getting very compact with every single generation. However, it was interesting to understand how this formation of every single generation is changing the shape of the polymer in comparison to dendrimers, for which we already know very well that with increasing generation number, they still have an open core which can, for example, encapsulate guest molecules. In order to understand this behavior, we used static light scattering and intrinsic viscosity. Static light scattering and particularly the analysis of the Zim plot can give us three values: the molar mass, the radius of duration, but also the second virial coefficient. And the second virial coefficient is directly coupled to the interaction between the segments within one macromolecule. Therefore, it can be also described with this equation in which the interpenetration parameter is taken into account. The intrinsic viscosity, in terms of Flory-Fox equation, gives us the dependence between the intrinsic viscosity and the radius of duration as well as the molar mass, and the correction factor within this equation is actually the Flory parameter or the drainage parameter, while the interpenetration parameter shows us how two polymer segments interpenetrate with each other. Here, the drainage parameter shows us how the solvent molecules are interpenetrating or draining into the outer shell of a polymer coil. Now, taking these two parameters or the ratio of these two parameters into account, we can obviously calculate and describe the segmental density within one macromolecule. This means that we have to take the ratio between the second virial coefficient and the molar mass and the intrinsic viscosity. Taking into account this ratio and plotting it against the generation number, we obtain directly information of the segmental density of our structures. Within the first zero generation, the first core, hydrobranch cores, we have rather fluffy structure, which is confirmed by transmission electron microscopy measurements too. Going to the first generation, we directly obtain a very compact structure, which means that every single monomer which is additionally included into the system fills out free spaces within the core. And after the next several generations, we still have very compact structure, but obviously the dendrons are growing on the top of this very dense core of the first generation. So increased segmental density in the core is already done during the formation of the first generation. Now we can go, based on this knowledge, to the conformation and quantification analysis of complex biomolecular systems. Now I will start with the conformation analysis of biomacromolecular systems, which is very important in terms of bio-nanotechnology, for example. Bio-nanotechnology defines the progress within synthetic biology, macromolecular biology models, and they have to deliver solutions for biometrics and theranostics. A lot of these systems are based on multivalent carrier systems, which are based on macromolecules, and these macromolecules are coupled with different type of peptides, antibodies, nucleic acids, drugs, and so on. This coupling can be covalent, but it could be also non-covalent, which is mostly the case. And the non-covalent binding is the main issue to characterize using separation methods and different detection techniques. Now we are working indeed with biopolymer systems or biomacromolecular systems in which a very pronounced polydispersity is existent. This means that we have big macromolecules combined with small drugs, or we have different bioconjugate or biohybrids in different sizes, or we have even much more than 2 components within one system. These systems are in most of the cases responsive against external conditions. We have to understand the conformation depending on the situation and the state they have. We have to quantify the amount of drug, for example, and we have to understand the self-assembly of these systems. Asymmetric flow field for fractionation is a method which can help us to understand a lot of these particular properties of these biomacromolecular systems, because this operation, as I already explained before, is working according to the diffusion coefficients of the different sized particles or macromolecules. Additionally, we have here very weak shear forces which allow us to understand and to characterize complexes in which the interactions are with 2. And we can very easily change the element as well as to characterize using different detectors, molar mass, size, distribution, shape, and to quantitatively characterize also, for example, the amount of encapsulated drug. This means that asymmetric flow fractionation has to be coupled to static light scattering detection and also to dynamic light scattering detection in order to obtain our conformation parameters in terms of scaling, exponent, as well as the raw parameter. In my first example, I will show you a rather simple system which is consisting of only one component, a dendronized polymer with a lot of functional group on top of it. A dendronized polymer is consisting of a linear chain and dendrons, as I already explained. The linear chain in this case is a maleiimide copolymer, which has 2 functionalities at each polymer unit. These functionalities are additionally modified with maltose units. In the first generation dendronized polymer, we have lysine with additionally 2 other functional units, which means that we have already 4 maltose groups for every single dendrons or every single polymer unit. This amount of functional end groups increases at every single generation. Now, what we expect is that the interaction properties of these polymers are strongly dependent on the amount of functional groups. What we found out by using AF4 and static light scattering is the aggregation number of every single generation of DEN poles. Surprisingly, the aggregation number was absolutely not depending on the generation number, but it was depending on the pH value, at least for the 0th generation and for the 3rd generation. This surprising behavior was explained after detailed AF4 static light scattering measurements with the shape of the different generation. While in the 0th generation we have a helical shape in which the density of the functional groups is very high, and these functional groups are exposed for further interactions. In the 1st and the 2nd generation, this helical structure is disturbed, leading to coil-like structure in which the functional groups are not completely available for further interactions. But in the 3rd generation again, the amount and density of dendrons along this linear chain is so big that we have, because of spherical reasons, also a stretched-like, worm-like structure on the top of which the functional groups are again exposed for further interactions. This information came indeed AF4 combined with static light scattering and additional complementary cryo-TEM measurements show us that 3rd generation DEN pole can behave as a rod-like structure if we have a pH of 11, and can have a coil-like structure if we have a pH of 7. And this kind of single monomers can aggregate with each other either in lateral aggregates or in dense sphere aggregates, depending on the pH we have. Finally, this kind of combination of techniques gave us a full picture of the shape of single polymers and aggregates depending on concentration, generation, and pH value, which can be explained with multifunctionality and a very strong multiple H-bond interactions between the polymers. These multiple H-bond interactions, especially in the 3rd generation polymer, can be explained with a huge amount of maltose groups only on one dendron short here. And these multiple functional groups can be also used for further interactions with other natural materials, which, as we showed on basis on cellulose nanocrystals, in which the combination of dendronized polymers and cellulose gave us supercolloidal structures, which can be further used based on all these measurements for the developing of lightweight materials and very good mechanical properties. Now I will show you another example in which two components are combined within one system. The one of them is a synthetic dendrimer, which is functionalized with maltose units in order to obtain a non-toxic and well-soluble in water dendrimer. And additionally, it is functionalized with biotin units. While biotin is well known to very strongly interact with avidin, with the strongest known non-covalent interaction. I think the dendrimers with different amount of biotin unit, 1 or 2, with different amount of avidin, we expect to obtain bioconjugates with tuned structure. AF4 combined with static light scattering unlocks a lot of information about these bioconjugate structures. First of all, we found out that we don't have only the well-defined bioconjugates we expect to have, but we have a very diverse structures within one sample, starting with the single components and going up to the well-defined bioconjugates, but also having very strongly branch structures as well as network-like structures. Finally, we found out that the conformation of our structures is very well defined, starting from linear type of bioconjugates, going up to less branched or strongly branched structures with very compact conformation, and going up to microgel-like conformations. All this information was available after analyzing the raw parameter from the dynamic light scattering and the static light scattering compared to AF4, showing this transformation of the structures with the molecular weight from a linear through very dense branched structures up to microgel-like structures, which is in a very good correlation with the apparent density, which we can calculate using this method. After showing you the advantages of AF4 combined with light scattering detections for the conformation analysis of complex biomacromolecular systems, I would like now to go to the last section of this webinar, the quantification analysis of complex biomacromolecular systems, not only by using light scattering, but also using RI and UV detection. First example is based on Polymersomes, which are vesicles based on components similar to liposomes, which have hydrophobic and hydrophilic parts. In this particular case, we have polymers with copolymers with hydrophobic and hydrophilic parts, which can self-assemble, building polymersome vesicles. These polymers are cross-linked, so that depending on the pH value, they can shrink or open their membrane, allowing penetrating of small gas molecules. Polymersomes can be used, for example, as nanoreactors if they are encapsulating enzymes or catalysts. In this particular case, I will show you an example of myoglobin encapsulated in a polymersome, which is able, depending on the pH value, to transform guaiacol into biphenolquinone. The question appears how much myoglobin molecules can be encapsulated within one polymersome. In order to answer this question, we use again AF4 coupled to static light scattering, but especially to UV detection, in order to detect the myoglobin and also the polymersome. Myoglobin and polymersome have very different sizes. While myoglobin has about 17,000 Daltons, polymersomes have very big sizes of much more than 100 nanometers. UV detection of the myoglobin shows a clear signal, while the polymersome give us with or without myoglobin the same signal. This means that by detecting the residual myoglobin which is not encapsulated into the polymersomes, we can back calculate the amount of encapsulated polymersome. For this purpose, we have first to calibrate the UV signal area in order to obtain quantitative analysis of the free myoglobin. This quantitative analysis gives us directly the encapsulated myoglobin via this UV detection, showing that we are able to obtain up to 60 myoglobin molecules encapsulated in our polymersome structures. Now, myoglobin is a relatively big molecule compared to some drugs which are very interesting to be analyzed quantitatively about their interaction with polymers as hosts. So host-guest interactions between polymers, for example, polyethyleneamine, which is functionalized by Maltose units, can complex Rose-Bengel, for example, as a model substance for a drug molecule, which is very small, with a molecular weight of about 1000 grams per mole, and using AF4 is penetrating the membrane. Now, polyethyleneamine can encapsulate Rose-Bengal, for example, at pH 6.7 and can release it again at higher pH values. The question is now how much Rose-Bengal molecules are complexed within this polymer. In order to answer this question, we again used AF4 with two different detection methods. The first detection method was to obtain information about the Rose-Bengal molecules which are penetrating the membrane during the focusing flow as the residual Rose-Bengal which are not complexed within the dendrimers. And the second way was to use the increase of the molar mass in the complexes in order to calculate the encapsulated Rose-Bengal molecules using the mouse detection. Independently on the detection method, we see very good agreement of the results. When we take a UV detection of the penetrating Rose-Bengal molecules during the focusing step of the separation, we obtain the same amount of residual Rose-Bengal molecules which are encapsulated within the dendrimer in correspondence with the increase of the molecular weight with the green points here of the complexes, showing that we have about 250 Rose-Bengal molecules per polymer, depending of course on the ratio we are preparing in the batch. With this last example, I'm coming to the last slide of my presentation and would like to summarize the different information I gave you today. First of all, size exclusion chromatography and asymmetric flow, field flow fractionation can give fast and reliable separation of molar masses within one injection for further conformational analysis. The combination with light scattering and viscosity detection gives us valuable information on conformational diversity, not only macromolecular structures, but especially valuable information in biomacromolecular systems in which several components are existing within one system. AF4 specifically with multiple detectors is essential method for analysis of biomacromolecular systems because AF4 can separate in broad molar mass range. We have a weak shear forces which gives us the possibility to characterize complexes with very weak interactions, and we are able to quantify gas molecules in host gas systems. Finally, I would like to thank to the polymer separation group, which is producing all these exciting results. Of course, I would like to thank also to all the institutions and organizations sponsoring our research. I would like also to thank to my colleagues at the Institute of Polymer Research and to all colleagues outside of the IPF with which I am working. I would like to thank you for your interest and will be happy to answer your questions.
Thanks for the fantastic presentation, Albina. Now we're ready to take questions. Here we begin the Q&A. And the first question I have is, you showed three methods to determine polymer conformation, SLS, ELS SLS, and viscometry SLS. How do you know which one to use? If the results of two methods do not agree, which is most likely to be correct?
Yeah, thank you very much for this question. This is quite important, actually. And theoretically, the values which we are obtaining by these three methods should be comparable. I mean, the information we are obtaining should be comparable. Especially this is valid for using the scaling law and the Kuhlmann-Howing equation, where the scaling exponent is actually arithmetically transformable into the Kuhlmann-Howing exponent. Now, it could, of course, happen that we obtain different results or results which are not compatible with shape of macromolecules or any particularities which we are expecting. One example is was shown during the presentation, and these were the dendronized polymers, which are giving us, for example, a scaling exponent of 0.25, which is actually rather typical for compact sphere-like structure. And without the microscopic investigations, which were complementary to these investigations, we were not able to understand why we are obtaining sphere-like structures out of worm-like polymers. Finally, the microscopy as a complementary method showed us that we are able to obtain lateral aggregation of these worm-like structures, which result in the same exponent value as a hard sphere. So finally, without taking into account some complementary methods, it is not really possible to understand why different results could differ from different type of scattering or viscosity calculations.
Okay, thank you. Next question I have here is, how is degree of branching determined and quantified? Does this analysis correlate with other methods for quantifying branching, such as NMR or FTIR?
Well, the degree of branching cannot be directly quantified just by separating and light scattering or viscosity detection indeed. This is possible only if we have any comparison with other structures with the same type of chemical characteristics. What we did for the samples I showed during the presentation, and namely the hyperbranch samples or the pseudo-dendrimers, we obtained indeed the information about the branching degree directly from NMR calculations. So we did indeed an NMR spectroscopy for every single sample and calculated the degree of branching by equations which are used to calculate the degree of branching of hyperbranch samples as the equation of Frichet or equation of Frey.
Okay. Just wanted to remind the audience that if you have any questions, that we'll be taking them, but you can enter them into the Q&A box, and we'll answer all your questions. So another question I have here is, you quantified the host gas complex encapsulation of small molecules in terms of the number of Rose-Bengal molecules per Polymersome in two ways: by analyzing the peak area of small molecules passing through the AF4 membrane, and by the increase in molar mass of the complex. Which method do you prefer? And do the results depend on experimental parameters such as flow rates or dilution during separation?
Well, the experimental parameters are actually easy to be optimized. That's not really the problem in such kind of systems. I think that, well, if we are considering calculation of the small drug molecules, or in this case of the Rose-Bengal molecules during the elution phase, it will be indeed not really easy because of a slower concentration of these molecules, which can be collected after that, penetrating the membrane. Therefore, we are using here the focusing step, where at once, very fast, the small Rose-Bengal molecules can be penetrated through the membrane and can be very well detected. But the actual problem here is actually if we can calculate the amount of drug molecules or Rose-Bengal molecules, and if we have enough Rose-Bengal molecules which are encapsulated within one polymer, so that we can obtain measurable increase in the molar mass during the elution step and the mass detection of the polymer. In this particular case, we had quite a big amount of molecules which are encapsulated by the polymer, so we had really measurable increase of the molar mass, and mass was quite suitable to obtain this information additionally to the UV detection. But in case for encapsulation of only several small molecules, for example, which can be the case, it is indeed possible to have two 5 or only 10 drug molecules within one big polymer molecule, which doesn't lead to measurable increase of the molar mass. In this case, we are limited only to the one method using the penetration through the membrane, of course. One example was shown actually here, not with small molecule, but with the myoglobin encapsulated in the Polymersome, where we can see a very clear decrease or increase of the signal of the single myoglobin, but we cannot see any measurable increase in the molar mass of the Polymersome with or without myoglobin. So this is the case where only very few myoglobin molecules are incorporated in such a big particle, and the increase of the molar mass is just not measurable enough in order to obtain information by this means.
Thank you. Question I have here is, how does the sample concentration affect the measuring results?
The sample concentration in which method generally, or you mean within these methods which are where we are using scattering, viscosity, and all these results? If you mean this one, actually we need the concentration of the sample in order to obtain information about the radius of duration, about the viscosity, because all these values can be calculated from the concentration of the sample. For example, intrinsic viscosity can be calculated only if we have a connection between the concentration and the specific viscosity for every single fraction. And taking into account the concentration with a signal we are obtaining, the relay ratio we are obtaining from the mass detection, we can obtain information about all other parameters as molar mass, radius of duration, as well as the secondary coefficient. So concentration is, of course, very important in all these methods for the characterization, finally. I hope that this was the right answer. I understood the question properly.
Okay, if that doesn't answer the question, then feel free to resubmit that question more specifically. So thanks, Albina. Here's another question for you. You combine multiple instruments, detectors, and fractionation. How difficult is it to combine all these and analyze the results?
Well, first of all, there are some parameters which has to be taken into account. Of course, that the combination is not difficult, but it has to be optimized, of course. In terms of technical complications, actually, size exclusion chromatography or field flow fractionation work very well combined with RI detection or with mass detection. Having viscosity detection, for example, with chromatography is also not very complicated. There are methods which are meanwhile very well known and trivial, and there are a lot of publication and technical support there in these methods. What is not really trivial is actually to combine field flow fractionation with viscosity detection. These are only few results reported, as well as I know on this topic, and this problem comes from the pressure which is produced during the focusing and elution phase during the FFF fractionation, which are changing because the pressure is actually the parameter which is measured in a viscosity detector. This makes this measurement not really easy, and therefore we are not using such kind of combination. So field flow fractionation combined with static light scattering, RI detection, or DOS is rather usual in our lab, but we are not using viscosity detector because it's not really not really easy, but not impossible, obviously.
Great. This question says, when you use AF separation, the fractions be collected for offline analysis?
Of course, yes. You have to have enough time, and sometimes we have to repeat the injection several times in order to obtain fractions in amounts which are enough big to perform other analysis. There are different reports on this. Indeed, it is possible, but you have really quite big effort to do this, but it is indeed possible. And there are some tricks which can be done, for example, overloading the channel, which means that using big amounts of sample during the injection. But this is, of course, a disadvantage for the separation quality. So sometimes it's better to take smaller amounts during the injection, but that make several injections in order to obtain the fraction of different elution times, and finally to have enough amount for further investigations.
It looks like we have time for one last question, and that's besides light scattering and what other detectors can be used with AF4, and what can we learn from them?
Well, what we are using is, of course, the light scattering in these two different modes, dynamic and static light scattering, and they're really, really very important for molar mass determination and size determination. And as I said before, without RI or without concentration detector in general, it is not really possible to use them. One another detection, concentration detection, is the UV-vis detector, and UV-vis is, as I showed before, very important to obtain information about samples which have a certain absorption, which can be, for example, used in order to obtain information how much of certain component is included in a system, which probably has another absorption maximum properties. And this is quite important if we are working with bio systems, because in most of the cases there we have indeed a UV activity which is special for certain polymers. Well, these are the techniques we are working with, and I think that they are quite important to obtain all the information needed for quantifying and for several substances in one, several components in one system, or to obtain information about the size and density of conformation of macromolecules and biomacromolecules too.
Okay, fantastic. Thank you so much, Albina, for your fantastic presentation, and thank you, participants, for being a great audience. Thank you, Wired Technology, for the sponsorship that made this interactive webcast possible. For CNN Webinars, I'm Linda Wang. Goodbye.